Okay, so part three of our look at stellar spectra was the application of um, of looking at the star spectrum and some of the things that we can find out from that. So we're really looking at understanding stellar spectra as an overall, rather than looking at individual skills. Here is the example. This is a stellar spectra that is taken from the Sloan Digital Sky Survey. This is real scientific data that we really use in astronomical and astrophysical research. So to recall, by finding the peak or by matching it to other stellar spectra, then we can find the temperature, and by looking at spectral lines, probably the most important thing we can do is find the composition, what's actually the star is made out of. There are a couple of other applications. One of those is that if we look at that composition, we look at what the elements are present. And a scientist, an astrophysicist, is interested in the amount of metals, the metallicity of the star. By the way, astrophysicists have a somewhat different definition of metal to chemists. To an astrophysicist, a metal is any element in the periodic table that is not hydrogen and is not helium. So everything else is metals. And the reason for that is that the early universe only created hydrogen and some helium. That was it. Every other element that has ever existed came about through stellar nucleosynthesis and was formed in stars. So if you look at how much of those other elements is present, that gives you an idea sort of the age of a star, or more accurately, the generation of a star. Was it one of the first stars to shine? Was it a later generation? The data for our sun is 73% hydrogen, 25% helium, and 2% metals. Some people think a little bit less, but that's the currently accepted data. And 2% actually makes our sun quite metal rich. Now, there are stars out there with more metals, but that still puts it into the population 1. And a population 1 star means it's a relatively young star, which means that it's formed from material that was created in at least 2, maybe 3 or more generations of previous stars. If we look out there in the universe, we also find many stars that are much more metal poor, and these are obviously older. They're second generation stars, perhaps. They have some metals, but they don't have a lot. And if we search very, very hard and look way back in time, which we do by looking very far away, then we find some very metal poor stars, and the suspicion is that these population 3 stars are primordial, or were formed from material that was basically had not been through stellar nucleosynthesis. It was virgin, new material at the time of these stars' creation. Most of the very, very first generation of stars, and we'll talk about this later, were very large and died very young and a very long time ago, when large parts of the universe were perhaps still opaque. But some, maybe, we are able to observe. This picture is of a globular cluster. Globular clusters are genuine clusters of hundreds of thousands to millions of stars which orbit ours and other galaxies. They don't have any material really left in them to create new stars. So pretty much every star in this picture that you can see belongs to this globular cluster, and pretty much every star is this orange colour of an old star. It has to be an old star, because any younger stars would have disappeared, died by the time that we get to take this picture. So only the old stars are left. Another thing we can do is we can look at redshifting. Now, redshifting is derived from the Doppler shift, which you will have studied if you did high-level waves. If not, just think of it as this sort of change in the pitch of sound you hear when a vehicle or something goes past you. The same thing happens with light. It's caused by compression of the light waves in front of an object and the spreading out of light waves between an object. It's also caused by the radiation stretching as the universe expands. But basically, you can tell if an object is moving away from us or moving towards us. And here's some data which illustrates that. The lines either side of the spectra are where these lines would appear in the lab, or maybe in our own sun. And the lines in the spectra are where they appear in the corresponding galaxies. The spectrum of a galaxy is made from the stars that make up the galaxy, so it's very similar. And what this chart is showing is that the further and more distant the galaxy you're looking at, the more these lines are shifted, the more they're moving away from us, which is an important result for cosmology. But closer to home, one other application of spectral lines is to look for double stars that are close together, so we can't see they're really double, but because in this case we're aligned so that at certain times, twice each orbit, one star is moving towards us and one star is moving away from us, then the stellar lines that we can look at seem to be apart, together when they're moving crossways according to us, and then apart when again, because one line is blue shifted and one line is red shifted. So if we see this splitting and coming together of spectral lines, we know that we're looking at a double star system, probably very close together, which leads to very high orbital velocities, which means that we can see the red shifting. Okay, and the final application, but perhaps the most important one, is as the basis of stellar classification. If we look at a star, we can see what it's made from and we can see what its temperature it is. And that temperature itself is probably the most important thing, because we classify stars at the first brush according to their temperature. So here I have a collection of stars of different types. These are all adult stars. They're all stars in their what we call the main sequence when they're converting hydrogen to helium. The main thing that's different here is their mass. A bigger mass star is bigger volume and much, much brighter. It's giving out much, much more luminosity, has a much greater surface temperature. Okay? Our sun, by the way, is this sort of yellow G type star, as it's called. So MKGFABO are the main stellar classifications, and they're based purely on temperature. So if we use Wien's displacement law to measure a temperature, we can classify it. If we do it for our own sun, it's between 5,700 and 5,800 in Kelvin, which makes our sun a type G star. In fact, it's actually a type G2 star, because we can vary this. G0 is the hottest type of G star, 6,000. G0, G1, G2, G3, G4, G5, G6, G7, G8, G9, 5,200 Kelvin, K0, and so on and so on. Excuse me. So this chart shows you their colour. This is what we conventionally say. We say M-class stars are red, but they're not really red. Most of them aren't deep red. Most of them appear to be sort of light orange red. Interestingly, this is the stellar distribution, and there's a clear relationship. The cooler the star, the more common it is. 76% of all main sequence stars, or more than that, in our neighbourhood are M-type stars. Though, interestingly, not a single one of them can you see with the naked eye, because they're really faint. As I said, luminosity depends greatly on temperature. O-type stars are incredibly rare. B and A-type stars are pretty rare. But these three types actually form a good percentage of the stars we can see in the night sky, because they're so luminous you can see them from very, very, very far away. So temperature leads to O, B, A, F, G, K, and M. The letters are in this order because originally it was set up as a different sort of pattern, and once we found out more about stars, we reclassified it. The way to remember the order of stellar classification is by a very time-honoured mnemonic, which has only been modified slightly over the years. O, be a fine girl, or guy, kiss me. So O, B, A, F, G, K, M. And you are expected to remember this order, possibly by using this mnemonic or whichever version you prefer based on sexual preference. But that's not the only thing we can find out from the sparse spectrum. Different sizes of stars here, and the much larger stars, because as a star ages into the next, its post-adult, its sort of old age, most of these types of stars expand greatly. Determines the gravity at the surface. The very large stars, the very, very large stars, have very weak gravity at the surface, and that actually makes a difference to the spectrum that you can see. The lines are a different shape, they're a different depth. And so we can determine the luminosity class, as we call it, of a star just by looking at the spectrum. Okay, and these luminosity classes go from really, 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 really big stars, type 0 or 1A plus, type 1A, 1AB, 1B. Type 2 and even type 3 are big, big stars. You have type 4 stars, which are the main sequence stars, ordinary, boring stars like our own. Well, they can be a lot bigger and they can be smaller, but they are burning hydrogen into helium. They're main sequence stars. And then we have two other categories which we'll be looking at in a lot more detail later, particularly the white dwarfs. So this is the kind of information that we can get. For example, so this is a breakdown of the different F-type stars, F0 through to F9, and the V at the end refers to the luminosity class V. So these are main sequence stars. Their temperature, 7,200, their mass, because we know it's a main sequence star, we know that it's a dwarf. The stellar category gives us a temperature, it gives us a mass, and it gives us the brightness. Absolute magnitude is the measurement of the brightness of a star as seen from a certain distance, from 10 parsecs. So that's basically the information that we can get from the spectrum of a star.